A bar magnet is hung by a thin cotton thread in a uniform horizontal magnetic field and is in equilibrium state. The energy required to rotate it by 60 degrees is W. Now, what is the torque required to keep the magnet in this new position? Let us first understand the concepts. We are given a bar magnet which is rotated at 60 degrees in a uniform horizontal magnetic field, and the energy required for this rotation is W, and we need to find the torque required to keep the magnet in this position. The potential energy U of a bar magnet in a uniform magnetic field B is given by the formula U is equal to minus mb cos theta, where m is the magnetic moment of the magnet, b is the magnetic field strength, and theta is the angle between the magnetic moment and the magnetic field. Initially, the bar magnet is aligned along the magnetic field. Theta is equal to 0 degree. So, the initial energy is given by U1 is equal to minus mb cos 0 degree. Since cos 0 is 1, we get U1 is equal to minus mb. After the rotation of 60 degree, we have U2 is equal to minus mb cos 60 degree, which is nothing but cos 60 is 1 by 2. So we get U2 as minus mb by 2. The energy required to rotate the magnet by 60 degree is the difference in energy. So we have W is equal to U1 minus U2. Here U1 is minus mb minus U2 is minus mb by 2. So we get W is equal to mb by 2, which implies mb is equal to 2W. The torque tau on a bar magnet in a magnetic field is given by the formula tau is equal to mb sin theta. For 60 degree, we get tau is equal to mb sin 60 degree, and sin 60 is nothing but root 3 by 2. So this implies tau is equal to mb into root 3 by 2. Now substituting mb as 2W, we get tau is equal to 2W into root 3 by 2, where 2 and 2 cancels, so we get W into root 3. The torque required to keep the magnet in this new position is nothing but W root 3. Thus the correct option is D.